Hi, Tom Walls, Carbide Processors. In this video I'd like to talk about the difference between theoretical and actual melting points of braze alloy. Starting with the theoretical. This is the AWS, American Welding Society, official book of melting points of braze alloys. This it's cost me $35, which is, this isn't germane, but which is about a little over $1 a page. Pretty good deal. Anyway, I had a customer call. We sold him some braze alloy that had a melting point of 1305 degrees Fahrenheit. This guy's a really good engineer, really good lab, big company. He put it in an oven, ran it up to 1305 degrees Fahrenheit, let it cool, and the braze alloy didn't flow. He wanted to know why, and this brings up a bunch of things, and I've done a blog post on it which may do a better job explaining than I do in this video. But he had used a couple of different braze alloys. He'd used bag 3, which is a 50% with cadmium, had a melting point, a liquidus point of 1270 degrees Fahrenheit. When they ran the oven up to that point, it melted. But he wanted to use a cadmium-free braze alloy, so we suggested a couple, and he went with a bag 24, which is a 50% braze alloy without cadmium. The first alloy, the bag 3 with cadmium, incidentally, bag is BAG-3. B stands for braze alloy, AG stands for silver. And this is the way the American Welding Society classifies alloys. Anyway, different alloys have different chemical compositions, and because they have different chemical compositions, they melt differently. Some alloys hit temperature, melt, and flow. Some alloys hit temperature and start melting and then flow out. These alloys that flow out slowly are sometimes referred to as gummy, which makes a lot more sense if you're brazing and actually trying to move the parts while you're brazing. That's one of the reasons. Another reason is that when the braze alloy hits the temperature, I call it 1305 Fahrenheit, when it hits that temperature, you still have an issue with the heat of transformation. It takes a certain amount of energy to change from a solid state to a liquid state. If you drop an ice cube into boiling water, it doesn't turn into water immediately. It takes it a bit. There's kind of an insulation effect in there, and if you're a really good engineer, I apologize. This is going to be horribly oversimplified. But anyway, think of an ice cube as having a lot of layers like an onion. It's not right, but think of it that way. As each layer has to get hot enough and then have a little more energy so that that layer turns into water before you can affect the next layer, and so on all the way through, which is kind of the reason why it takes a while for an ice cube to melt, even in boiling water. Another factor that can affect how the braze alloy melts has to do with the assembly and how you're heating it. So it's going to take longer. It's going to take a while for the heat to get to the outside of it, or get to the inside of an assembly. I found this. This is a carbide tipped. This is a carbide tip lathe tool. It's a cheap lathe tool from Sears. I made this, I don't know, 10-15 years ago. But anyway, the outside gets hot, and it takes a while for the heat to get from the outside to get to the middle. It doesn't take too long on something this small, but this is a piece of carbide. This is a Debarker tip. Debarkers take bark off of logs, which is really important in a sawmill because you want lumber and you don't want bark in your chips. So this is a really big piece of carbide. If you put this on top of a big piece of steel and start heating it with a torch, or if you put it in an oven and heat it, it's going to take a while for the heat to get all the way through to the middle. As an aside, if you're doing this, braze alloy comes in several forms. This is a ribbon. Yeah, you can see it. It's a ribbon. That's what it looks like. Comes in various widths. This is a wire, which is used more often than the ribbon because the wire is cheaper. But it's common to take, with the big parts, it's common to use a ribbon, particularly a tri-metal ribbon in between. So you take the piece of steel, which is this hand, you put the braze alloy on it, then you put your carbide part on it, then you heat the whole thing up. Part of the reason to do this is there are ribbons that are tri-metal with copper in the middle, which helps relieve the stress caused by the difference in coefficients of expansion. A good trick, if you're doing this, is to take a little piece of wire, put it on top of the ribbon, and then put your part on it. That way the part sits up a little. When the wire in the middle hits temperature, it flows out and the part settles down. That way you know you've got the piece hot all the way through. Now that I look at it, yeah, you can see it. These are two different pieces, two different pieces from two different kinds of braze alloy, and you can see that there's a difference in the flow patterns. In this case, it's not a huge difference because of the way we prepared it, but this one flows out, so it's a lot smoother and flatter. This one actually has a hump in the middle. The ones I'm rubbing, so a hump in the middle, a lot smoother and flatter. So if you're used to seeing this kind of a flow, you switch alloys and get this kind of a flow, it's going to be a surprise. But that's the way the braze alloys work. What else? Let's see, hang on just a second while I check my notes. Issues braze melts at a given temperature. Surface preparation can be critical. If you have a dirty surface, if you have free carbon on carbide, if you have oils or greases on steels or other metals, you can get the braze alloy will go from flat or a wire ball up like spitting on a grill. Strangely enough, apparently everybody in the world has spit on a grill at one time or another and watched it run around. But braze alloy will do that if the surface isn't clean, so that can affect how it flows out. The only real figure I've seen between theoretical and actual practice was in a NASA tech brief decades ago. They used the figure 50 degrees Fahrenheit. So if the theoretical melt point is 1305 Fahrenheit, you add 50 degrees and go up to 1355 Fahrenheit. If you're really, really temperature sensitive, you can take your oven up to 1305, hold it there, and then let the energy soak. Oh, there it is. Let the energy soak in, and what happens there is the energy soaks in so that the middle eventually gets up to the 1305 too, even though it's insulated by the rest of the assembly. 1305 is a rule of thumb. It's a good rule of thumb. It works really well in actual practice too. So that's some of the reasons why there is a significant difference between the theoretical melt points and what you're going to see in actual practice. Thank you.